Hi everybody, welcome back to the Feynman technique. Today we're going to solve this integral, and this is going to connect to the previous video where I proved that the sum of the reciprocals of the squares is equal to pi squared over 6. So this integral resists standard integration technique, so we'll use Feynman's technique, or differentiation under the integral sign, by introducing a parameter t, but not in the usual way. This is going to be our f of t. And now this does not look like our original integral. So up until this point, typically our solutions involved parameterizing in such a way that it would very closely resemble our original integral. In this case, it doesn't. In this case, we don't have the natural log x, but the natural log x will appear when we take a derivative. Um, it also may seem strange that I included this -1 here. That instead of just having this be the integral from 0 to 1 of x to the t over x minus 1, and the reason for that is that it would not converge for any t if we did that. This is convergent for, well, let's see. I'm not sure exactly, but this does converge for values of t that we need it to. Specifically, we will need it to converge at 0, which it does. It equals 0 when t is equal to 0. All right. And next thing, what we're going to do now is we're going to differentiate under the integral sign. And differentiating under the integral sign recovers a natural log x, which is exactly what we want to be there. But we have this x to the t. Well, that can be dealt with by letting t equals 0. If we set t equals 0, we recover our original integral. So f prime of 0 is equal to I. All right, well, great. So what have we really done? Well, we can express 1 over 1 minus x as this sum right here. And then we just split up the numerator here. And we can express this just like this. Okay. Well, that means we can put an integral from 0 to 1 dx in front of this because it's equivalent to this. So that's what we do in the next step. So our f of t is actually equal to this. Okay. So now what we need to do is we're going to need to switch our integral or our integration and summation. And we can do that because there's not going to be a problem with convergence when you do that. All right. So this is what happens here. If we switch these two symbols right here and we integrate this from 0 to 1, here's what happens. We get the antiderivatives from 0 to 1, which evaluate to exactly that. So there is f of t, but we don't care about f of t. We actually want f prime of t. So we can take a derivative with respect to t of f of t, and notice what happens. This whole part right here has no t's in it. So it's going to drop out when we differentiate with respect to t. And this is what we get. This is our new sum after we differentiate with respect to t. So this is f prime of t. Now we know that I, our original integral, we said was simply f prime at 0, right? Where did we show that? Let's see. Yeah, right here. F prime of 0 is equal to I. So now we just set I equal to f prime of 0 is equal to this. And that is exactly the sum of the reciprocals of the squares. See, if we take this, our f prime of t, and evaluate it when t is equal to 0, we get the sum of the reciprocals of the squares. And in our last video, we showed that that was equal to pi squared over 6. So that is the answer. This integral is equal to pi squared over 6. All right, guys, I hope you enjoyed that, and we'll see you next time.